Computational Fluid Dynamics by Mr. S. Nagarajan, Managing Director, Flow Expo, Coimbatore. Mr. Nagarajan, S. Nagarajan has 10 years experience in computational fluid dynamics, having served in major industries in India like DRDO, General Motors, Cummins India, LMW, Pricol Technology, etc. Now I hand over the session to Mr. S. Nagarajan. I welcome you, sir.
Thank you so much. Thank you so much for this great opportunity.
Thank you.
Yeah, good morning to everyone. And myself is Nagarajan. I'm the Managing Director of Flow Expo. Basically, Flow Expo is a kind of consultancy services. We provide consultancy solutions to abroad as well as Indian companies in CAE. And we do staffing solutions to most of the companies starting from Cummins Pune, Johnson Control, then Renault Nissan, kind of automotive big giants. And today's session, it's a kind of introduction to computational fluid dynamics. And I don't know how far I can go in this session, but maybe in the near future, we can continue this session. And it is scheduled for 1 hour. Maybe I can continue the entire session for 1 hour. Conversation, is it audible?
Yes, sir. Yes, sir.
Okay. Yeah, it's, let's turn towards the history. You can go to slide number 1, slide number 2. Yeah, the next slide. Okay. So in history, there are a lot of incidents which really inspired me. And the first incident which I see, which really inspired me, is the first one. The Crusade War that happened in the English Channel in 1588, where it had been held between Spain and England. And that time, Spain was a dominant power where their ships were very rugged. They have big cannon with which they can destroy other countries. And United Kingdom wanted to prove that they are equal to the Spanish Navy as well. And that is a period where they want to prove that Protestant is more than Catholic as well. So Queen Elizabeth I called Galileo for designing the first Navy ship with which they want to fight against Spain. It was a very short period that Galileo had, and he made a hell lot of trials in the sea itself. And finally, he found the best one out of it. And he devised a beautiful small ship with which they won against Spain. That is a horrible moment because being a kind of greatest scientist, one of the greatest scientists, it is a tougher moment for even Galileo to devise such a kind of ship for, fight against Spain. Because it's a very short period. Without any notice, it came all together and he devised. That is a period where he found we want to devise an alternate method for experiments because doing experiments is really challenging. That too in sea, it's really challenging. And that is a period where world realized that they want an additional or alternate method with which they can completely remove the cumbersome, toughest experimental methodology. Yeah, you can go to the slide number 2, the next slide. Yeah, Congressman, you can go to the next slide.
Yeah, it will take.
Yeah, it's almost another 500 years. After 500 years, these two people, they found the first flying machine in the world. If you look into the history, even at the 16th century, everybody started off, thinking about the, flying machine. Even China did a lot of things. We could have seen a lot of things in history as well, like Ravana flight, Raman flight. But these two people, Wright brothers, they made things came into life. They really made a fabulous achievement in the world. Prior to that, they made hell lot of experiments with a lot of NACA profiles, with a lot of different profiles in test lab. The worst part is whenever they made a kind of successful attempt in experiments, when they come into life, it was unsuccessful. The successful trials they made in wind tunnel was really unsuccessful in real world. But fortunately, in 1902, the first flying machine was invented. Prior to that, these two people, they traveled to Germany, they met one scientist, they said like, even if it takes another 2000 years, we won't construct a machine which can fly. But it's quite fortunate because of these two people, they really made the first flying machine in 1902. So that is one fabulous achievement. And yeah, you can go to the third one. And this is a horrible moment. In 2003, even NASA launched the Columbia flight, and a lot of people were there, a lot of astronauts were there, and we were proud to say that Indian Kalpana Chawla was also there. But it was really horrible when that that came to a disaster moment. That was really a bad situation. Before landing, it got blasted. So these are the moments where people realize that conducting experiments really, really challenging, because experiments are really having a lot of difficulties. And apart from that, things may be useful, it may be really awesome, it may be working properly in the testing lab, but putting those kind of stuffs in real world is really challenging. I usually say, your safety relies on others' break. You can travel properly. You can travel according to the guidance of the Indian rules. But what is going to be the other person's mind? So you cannot travel. So testing things in test lab is really awesome. It can work properly. Your bike can give 60 kilometers per hour. Your car can give maximum fuel. It can reduce least drag. Your pump can give maximum efficiency. But if you put that into real world problem, it will be a tougher one. So that is where people realize that they want an alternate for these kind of cumbersome, tougher experiments. So experiments are really, really challenging. They wanted, if you want to, devise a methodology, devise a concept, devise a product, if you want to produce a product, if you want to invent a product, without experiments, without validation, nothing is possible. But to do experiments, people want to realize on experiments. Yeah, you can go to the next slide. Yes, this is a kind of a structure of an industry, even if it is a mechanical industry or electrical or electronic, whatever it may be. You have major 3 departments. The first one is called R&D, which is meant for producing conceptual design, the design from which people do from scratch. When pens are introduced into the world for the first time, it's a conceptual design. When flights are introduced into the world for the first time, it's a conceptual design. So you do develop a product from the concept. And once the product is launched, depending on the situation, depending on the customer's need, depending on its performance, you need to enhance the product continuously. You need to add some retrofitting continuously, and you want to add those kind of stuffs to enhance the product. That I can call it as design for development or design for enhancement. So whatever the product you develop, whatever the end application of the product, even if it is a small valve or if it is a valve applied in an air flight, or even it is a big flight or a kind of space shuttle, before putting into manufacturing, a huge level of manufacturing, there is one important phase which is called validation. So validation is very, very, very essential part. So even if you apply sophisticated instruments, sophisticated methodology, knowledgeable people to design a product, even if you invest a lot of money in prototyping, production, if you don't validate, if you don't test the performance of that, it will be absolutely waste. So you need to check whether it is working properly to the expectation prior starting the R&D. So order for diesel consumption or crashability. If it is a pump, you should know it should produce this much discharge, this much head. This kind of stuff one has to validate. So without validation, the production, R&D, everything is entirely waste. And if you look into the production area, you can think like the cost involved in the machine procurement is huge. The people involved is very huge. But R&D is the place where intellectual people comes into picture. The brainy people comes into picture. The money that is invested in R&D is really, really, really huge. So if you don't validate the product properly, whatever the money that you are investing in R&D is waste. So you cannot get it back. That means what I'm trying to say is like, you can invest too much money in R&D. That is a hidden cost. Like you cannot get it back. See, if you produce the component, you can sell it and you can get it back. But the money and the time span that you invest in R&D is absolutely irrecoverable. You cannot get it back. So the idea of the people who worked on design, who worked on R&D, who worked on development of a product, they want to reduce the time span, the money span that is invested in R&D. So for the sake of simplicity, I cannot say that R&D is only meant for the modern era. It was very old technology. When people rub the stones and they found fire, it's a kind of R&D. See, before 2000 years, logarithms were developed. Ships were constructed. So I thought like, ships aerodynamics is a kind of area, is a kind of era for Newton. But it was 2000 years old. People constructed beautiful yachts, beautiful ships. They travel around the world. They invented a lot of things in the era of 2000 years. So R&D is a kind of thing that is meant for 2000 years. When people initiated the life, R&D into picture. They could have taken their family in law with R&D. So R&D is an older era. So when they want to devise a new product, they want to completely rely upon experiments. So now the idea is something like you want an alternate for experiments. And with those experiments, you want to validate the working performance, the ability, the endurance, the satisfactory performance of the product. That is what we are interested in. Yeah, you can go to the next slide. Yes, I'm just giving some idea about what is experimental investigation. So the first picture shows how the aerodynamic performance of a car is tested. So you take a small number of, small cars which is manufactured in India, or any high-end cars, they put that cars into wind tunnel, which is something like 500 crores to 5,000 crores investment. Particularly cars like Formula 1 cars, they are really, really high-end cars. They want to put those kind of cars into wind tunnel, and they want to test it out for the performance of that car. Generally, they test it out for the fuel economy with a parameter called CD, coefficient of drag, CL, coefficient of lift, the fuel efficiency, the side moments, the tracking, the engine performance, everything has to be tested. So it's really, really, really challenging. And the bigger difficulty, what I'm trying to say is, it is altogether different. If you see that picture, the car is stationary, the wind is moving. In practical, the wind is almost stationary, but the car is moving. This is one such bigger difficulty of experiments. You need to do the experiments so that the experiment should really correlate to the real world thing. So this is one such difficulty of that. I'm again repeating. So conducting these kind of experiments for cars takes millions of money. And the next picture, what I'm showing is how the people test the pumps. So they put the pump in a test rig. There is a kind of pipe network. They put that into test rig and they test it out. So they'll draw a curve which is against discharge versus head, and they found out what would be the optimum point of working of the pump. Yeah, you can go to the next slide. Yeah, these are some kind of other instruments which will help you in doing the experiments. It's a kind of data logger and measure temperature, and there is something called PIV. So this will measure the velocity of any structure or any kind of room or anything like that. So these instruments are really costlier, and this is available in IIT in India. Yeah, you can go to the next slide. Yeah, you could see these kind of experiment methodologies. So the biggest difficulty in experiments is like, you need to create the prototype. You need to wait for every component to arrive at your end. You want to assemble it. You want to put that into test rig, and you want to test it out. So the bigger difficulty is, the first thing is it's very, very, very costly. Number two is it's time consuming. And it's always single purpose. What I mean by single purpose is, like, if you construct a wind tunnel, which is worth of say 5,500 crores or anything like that, you can test only cars or flight in those wind tunnels. You cannot test a pump. You cannot test another instrument. So experimental setups are meant for only that product, not for other things. And if you want to measure velocity, you want one probe. If you want to measure pressure, you want another probe. If you want to measure temperature, you want another probe. So these many probes are variables. So it's really challenging. And the biggest difficulty with the experiments is something like loss of insight. See, I'm testing one particular product. It has been tested. Let us take a simple example that you are testing a kind of pump in which the water is flowing inside a pipe and it is getting pressured up in the pump region. It is getting delivered. You cannot peep into that structure and you cannot see it. So you cannot get into that pump section and you cannot see what's really happening. Am I right? So if you don't check it out, if you don't understand what is really happening inside the structure, how can you understand that this would be the difficulty with which I'm losing some performance? So you cannot see what is really happening inside the system in experiments. You cannot understand the reality of that. So unless otherwise you understand what is really happening inside the system, you cannot come to a conclusion that if I want to change this, it is going to be improved. So ultimately you want to understand what is the problem inside that. I want to devise a methodology to overcome that. So if you don't understand what is happening inside the system, arguably you cannot go for the conclusion. You cannot go for the design change and loss of foresight. The biggest difficulty in the real world is, I'm sorry to say this, the fear of death. So every scientist had the fear of death. See, now Corona is spreading. Everyone is afraid. Everyone is panic. So the fear of death is not only for you or me or for any other. Even it is for Einstein. Even it is for Newton. So when they thought like, what's going to happen for the next moment? What is going to happen for the next year? What is going to happen for the 100 years? Even if I'm not there, they thought a methodology to devise what is going to happen in the future. That is called future prediction, time travel. So time machine is what we call. So time machine is not a kind of machine. It's a mathematical tool. So everybody wanted to design or devise or find something to understand, analyze. If they want to construct something, what is going to happen for that system after 100 years, after 20 years, after 30 years? What is going to happen for myself after 100 years? So that is what is called foresight. Experiments for that system. So experiments have these many difficulties. So people wanted to devise, scientists wanted to devise a methodology with which they want to overcome these difficulties. So I guess people are clear that validation is very, very, very crucial for modern day industry. Without validation, you cannot develop a product. developing product is very much needed. For example, when Corona is spread, people invested a lot of things to devise a testing methodology to develop a product which eradicate the spread of Corona. Even Bell invested a lot of money, a lot of thought to pump these sanitizers. You can see a lot of instruments here and there. So design is altogether an essential part. So when you do design, you need to validate. Validation has to be done for developing a proper product. Otherwise, R&D and production is waste. So to develop a product, you need to validate. To validate, you need only one. You have only one technology, which is called experimental investigation. Experimental investigation has difficulties, which I mentioned. So now the entire goal is scientists wanted to develop an alternate to experiments. They want to do, understand, develop the product with ease. They don't want to rely on experiments, but they wanted to have immense information that can be acquired comparing to experiments, but at ease, with very easy method. With minimum effort, they want to understand the product. Yeah, you can go to the next slide. Yeah, I guess it's again repeated. The slide is repeated. You can go to the next slide. Yeah, you can see some kind of experimentation methodologies. Like you can see one crashing testing. Yeah. So as I mentioned, every time you check the crash ability of the car, the cost of the car is lost. Even if it is 1 lakh car or 10 lakh car or 1 crore car, if you want to check the crash ability of the car, the cost of the car is lost. So that is a bigger difficulty you have with experiments. And you see the next picture, it's a big structure where the fire is on. So I cannot ask anybody to go and check the temperature when the fire is on. You can see, big structures are there, like maybe you can think 100 stories building. So when there is a fire in an office structure, you want to aggress people, you want to take the people out, and that is a very essential thing. At that time, how this fire is spreading, if at all there is a fire, how it is spreading, how the people can be evacuated from that particular area, because you can see different people. There may be a child, there may be an adult. So how the smoke is going to spread, how it's going to abruptly disturb the visibility of those people, how they can be evacuated from that particular area. So these kind of things are tougher. So prior to testing, people wanted to do this kind of experiments. So conducting experiments are really challenging for understanding the scenario. This is the worst scenario. This is really worst scenario. This is a hazardous situation. So you cannot do a testing prior to constructing those instruments. For example, if you want to understand when there is a dam break, how it is going to trouble the indentation which is on the particular area. You may have people living, you may have wind tunnels, wind mills, you may have other areas. So if there is a dam break, how it is going to affect the area? For that you cannot break the dam and you cannot see it. So this is one such difficulty. And you can see the third picture where NASA tested one space shuttle. That shuttle was traveling at a Mach number of 25, literally 8,000 meters per second, 8.3 kilometers per second. In 1 second, that space shuttle travels almost 8.3 kilometers. So it's really challenging to do that kind of experiments. You don't have any kind of wind tunnel in the world till date. So doing experiments really challenging. And you can see the other one, which is in the medical side. So this we call it as computational hemodynamics, wherein you can check how the blood is moving into the veins, how it is moving. It's flowing in the heart structures. So to understand these kind of stuffs, experimentally is really challenging. Till date, we have, a lot of, development in medical, but it is not possible with computational. Yeah. The next picture shows how people do testing even in NASA when a shuttle is moving. So it is really tougher. And you can see the pump testing once again. See how big the structure is. If you have a very big network of pumps, very big network of pipes, it is really challenging. For example, when crude oil is extracted from the extractant point till the delivery point, you have a big structure of network. A lot of pumps are there, a lot of pipes are there, a lot of valves are there, a lot of delivery points are there. It's really hazardous. So in which you have not only the oil, not only the crude oil, you have mud, you have wax, sometimes it get blocked. So you need to be very appropriately understand those kind of structures where the crude oil has to be delivered at the delivery point at the appropriate time. Otherwise, if there is a block, that will cause a big disaster. So experiments are always challenging. That is what I'm again and again and again repeating. Yeah, you can go to the next slide. Yes, so this is where my really session starts. So now you people understood what is the difficulty of experiments. Yes, what is an alternate for experiments? What is mathematics? Mathematics, a really, really challenging word. If somebody, heard a term called mathematics, they become really, tougher about it. So is mathematics a chiller or a killer? What is mathematics really? So is it an aid for, people, or what it is? See, we could have studied a lot of mathematics till 10th standard. But if we come to, +1 and +2, we could have studied algebra. Apart from algebra, we could have studied calculus, starting from differential calculus, integral calculus, analytical geometry. What is mathematics really? And once we complete 12th standard by mug-upping some kind of stuffs, and because of the immense pressure that is given by the schools, and once we come into colleges, again, M1 comes, M2 comes, M3 comes, and apart from that, probability comes. Now there is a point, like my engineering depends on how am I clearing the maths paper. Actually, maths 1 or 2 or 3 stands between my engineering and my marriage. If I finish my engineering, my father says like, you can get married. So the point is like, yeah, maths is found to be a kind of tougher subject for these engineering people. But to be honest, maths is not that one. So in one film, Vadivelu says like, I don't know, Vadivelu or somebody, like that, you have M1, M2, M3. For many people, M1, M2 maybe is easy. But for M3, it becomes an MN for them. Fine. So what is mathematics? So let us look into that picture. I've drawn a circle. So that is called diagrammatic form. The same circle can be very much stated as circle. That is a descriptive form. If you call that drawing as a circle, it is a descriptive form. And there is an alternate for it, which is called mathematical modeling. So mathematical modeling or mathematical form is a nickname for your structure. It's an alternate name for your structure. Nowhere it is going to kill you. It is going to aid the engineering. It is going to aid the science. It is going to aid the technology. It is going to aid the human society. It is not a killer. It is a chiller. The way we understand mathematics, the way we understand partial differential equation, the way we interpret mathematics is really challenging. But without mathematics, nothing would have been possible in the world. No science, no technology would have arrived. We wouldn't have a building to stay. We wouldn't have a car to move. We wouldn't have a flight to travel around. We wouldn't have a method to invest something. So mathematics is an alternate for a structure. So the same circle is converted into a descriptive form, which is called circle. It's a kind of name, and the same is represented in a mathematical form. So mathematical form, again I'm repeating, is a nickname for your structure, nickname for your geometry. So once you convert a structure, a shape into a mathematical form, that is called CAD conversion, CAD modeling or geometrical modeling. Is it clear? Yeah, you can go to the next slide. Yeah, so yeah, I can see two different era of mathematics. One is algebra, another one is calculus. So the people who on the left side, I mean right side, Newton as well as Leibniz, they are the trendsetters. They are the real changes of the world. Prior to them, there was one mathematical technology which is called algebra, and after Newton and Leibniz, there was something called calculus. So Galileo was most of the initiator, but this Musa was such a wonderful person who did a lot of things in algebra. Fine, we'll try to understand what is algebra and what is calculus, and we'll try to understand what's the difference between these two things. Okay, let us take a simple example. Yeah, you could have traveled in a bike or car. Let us assuming that I am moving in a bike from one place to another place. If somebody is asking, I mean, I've started from A, I traveled to B, I finished my traveling, and if somebody asks at what velocity or speed you have traveled, I'll say like around 40 kilometers per hour or 50 kilometers per hour. And these youngsters are doing a lot of stunts. They are traveling at say 100 kilometers per hour even. Now the point is like these values are not true. They represent average values. At every instantaneous location, at every instantaneous time, they could have traveled at different velocity. So the modern engineering, the modern technology needs only instantaneous values, not the average value. When Newton sat under the apple tree, when apple fallen, he thought why apple is falling? Why not moon? He had two questions. Why apple is falling? Why not moon? So with that question, he invented gravity. He took nearly 28 years to find gravity. And the second question is, he threw the apple back into the air, and the apple was continuously moving up and up and up. And at one particular height, it started to come down. Now the point is, he found the apple was not traveling at a constant velocity. The energy that I applied, which is in the form of kinetic energy, is keep on slowing, keep on getting down. It is decreasing further and further and further. And one particular height, the complete kinetic energy is lost. And again, the potential energy comes into picture and the apple gets accelerated. So he came to a conclusion that nothing is average in the world. I mean, you can represent everything in average, but the modern era, the modern description, the detailed description of anything is needed with the instantaneous values rather than average values. You can represent everything with average, but average won't, completely describe, completely realize, completely picturize the, the behavior of the structure. For example, if I want to understand how the air is moving inside a room, wherein I have, say, some heat sources. For example, I have a computer, I have some kind of electronical instruments which is generating too much of heat. Now my goal is I want to cool down the entire room. I want to know the temperature at each and every nook and corner instantaneously. If I say the temperature inside the room on average is say 40 Celsius, it's absurd. If I say the velocity inside the room on average is 2 meters per second, it's an absurd. If I have a fan, if I have a blower in one particular area, the velocity will be different. And if I have a hot spot in one particular area, the temperature will be high. So I should know where the temperature is maximum, where the temperature is minimum. According to that, I can plan the design. Otherwise, it's an absurd. So algebra is useful, but comparing to algebra, calculus is very much useful. Otherwise, the entire design won't be that much, effortful. Yes. So algebra invented before Newton and Leibniz. Yeah, Newton and Leibniz was the initiator. In fact, Leibniz did a lot of research than Newton, but Newton, he put things into practical application. Yes. So algebra operates on discrete variables. Calculus operates on continuous variables. It produces average results, but calculus produces instantaneous results. So you want instantaneous. For example, if you want to check it out, the behavior of the Ferrari, the same air is available in front of the Ferrari car. The same air is utilized properly to reduce the drag in front of the car, to enhance the combustion in the combustion chamber, to reduce the lift on the rear end. So the same air is available. How the design is made. So if you want to understand that thing properly, you want to know when and where the velocity is changing appropriately. You want to know the instantaneous values rather than the average values. Okay. Yeah, you can go to the next one. Fine. So I talked about experimentation, the difficulty associated with experimentation. The one such alternate for experimentation is mathematical modeling. As I give an idea how circle is represented in the mathematical form, people started to convert the physics into mathematical form. I'm living, that is physics. I'm talking, that is physics. Air is moving from one end to other end, that is physics. Fuel is burnt in a combustion chamber, that is physics. Fire is getting propagated in one particular area, that is physics. So everything is physics. So now every physics can be converted into a mathematical form in differential form, that is particularly partial differential form. So whatever the differential equation you could have seen in your 12th standard, you could have seen in your engineering mathematics like M3, that has a meaning, that has a meaning. They are not absurd equations, they have a meaning. They represent some physics. Even the universe was written by Galileo as a partial differential equation. So every physics can be converted into its own equivalent partial differential equation. All the partial differential equations are not absurd. They are not meaningless. They are very much meaningless. They have meaning. They have an immense meaning. They are meant for describing the physics properly. Okay. Let us take some simple examples. Say one-dimensional conductive heat transfer or three-dimensional conductive heat transfer or wave equation. So these are the simple equations, these simple examples which were converted into mathematical form. Maybe I can ask you to go to this next slide. Yes, yeah, this is the slide I want to have. So you can see a bar, a kind of metallic bar. On one end, you have one particular temperature. On the other end, you have another particular temperature. So let us assume that T1 is greater than T2. When they are in different temperature, obviously you bound to have temperature at every, you can call it, temperature will be continuously changing at different locations. So this physics can be descriptively explained as one-dimensional steady state conductive heat transfer. Now my goal is I want to understand what is the temperature at every point in that particular bar. If I want to understand what is the temperature at that particular bar at every point, I want to put those many number of probes. It is really challenging. N number of probes are introduced into that structure and testing those things and converting those information in a proper data is really challenging. For example, like what is happening in Corona case, you cannot do those many tests. If you test almost 5 crore people in Tamil Nadu, so maybe 8 crore people in Tamil Nadu, 138 crore people in India, how you are manipulating those data, how you are storing those data. So conducting experiments is really challenging. Now the same physics is converted into a mathematical differential form, something like dou square t upon dou x square. I've split that into dou by dou x of dou t by dou x is equal to 0. So this has a meaning. This differential equation represents one-dimensional steady state conductive heat transfer where a bar is kept at different temperature, and I want to understand the temperature distribution all along the bar. Now with some mathematical method, with mathematical manipulation, I found a solution, something called T of x is equal to C1x plus C2. So these C1 and C2 are arbitrary constants which can be very much arrived from boundary conditions. So if I get C1 and C2, just by applying the value of x, I can find the temperature at the bar, at any particular temperature, at any particular node, at any particular point. X is nothing but the point where I want to get the results. Just by applying the value, I can get the temperature. So you don't want to do experiments. You don't want to do any such cumbersome, tougher things. Just by applying X, you can get the immense results at any point, any location. And if you want to understand how the system is behaving as a function of time, if you are able to arrive an expression, something called T of x comma t, something like C1x plus C2t, just by applying the value for the t, you can get the result at that particular time as well. So if you apply t as 100 years, you can get how the system is going to behave after 100 years. So that is the beauty of mathematics. Mathematics gives an alternative to the experiments with least effort, and you can get immense results about that system properly, with which you can understand the system properly with ease. Yeah, you can go back to the previous slide. Yeah, the problem associated with this kind of mathematical modeling, in spite of having these much advantages, something like it is meant for only simple geometries. When the geometry becomes really complex, very terrifying, you cannot work with this mathematical modeling. It is meant for only simple physics, like one-dimensional heat transfer, two-dimensional heat transfer, particularly conductive heat transfer, wave equations. So on one hand, the experiments are really challenging. On the other hand, in spite of having these many advantages, mathematical modelings are have limitations. So what would be the other one? Yeah, you can go to the other slide. Next slide. Next one. Yes. Now you see some kind of structures with which we regularly work. These are really, really tougher real world models. The first one is a compressor. Then you have a container, engine structures. It's a rack assembly, which we work for DRDO. Most of the structures we work for DRDO. So these structures are really, really complex. And when these structures are put into ships or flights, when there is a kind of different movements, it will be challenging. The behavior will be entirely challenging. When the wavy motion is imposed into the Navy, ships, the behavior will be tougher. The truss structure also, you can see there's a very big truss structure. The stress concentration, the strain, everything will be tougher. So if there is any flaw in that truss structure, the entire system will collapse. You can go to the next slide. Yeah, you can see the other structure, which is something called a dashboard, which you can see in front of a car. So on name, it's a simple dashboard, but these structures are very complex. And you can see how an external aerodynamics of a car is tested. The car structure is also very complex. Yeah, you can go to the next slide. See, a lot of complex geometries are keep on, shown. The powertrain structures and the cabin cooling, wherein the people are sitting inside, how the AC is getting distributed inside the car cabin, how they are getting cool, that is essential, and engine assembly. Yeah, you can go to the next slide. Yeah, underground, it's a kind of underground assembly. Like you can see underneath the car, you can see a lot of structures. Again, in auto structure, we have a lot of other complex structures. So these pictures I'm showing just to, give an idea how the complex models are, real world models are really complex. They are not simple like what I mentioned in mathematical. You can go to the next slide as well. Yes, these are exhaust assemblies, after treatment assemblies, which we can see in our bikes or cars. So really challenging structures. Like for example, you see the exhaust gas comes into these structures in a shorter span of time. They has to be expelled out of the atmosphere with a no span of time, because the combustion timing itself is really small. And at the same time, you need to reduce the velocity of the air, the temperature of the air, the sound has to be reduced. These kind of tougher challenges are there. So that is where the design is really challenging. These models are really intricate. They are very complex, not like the simple models which I've mentioned in mathematical model. Yeah, you can go to the next slide as well. Some kind of pumps, some kind of external flows, like some bomber structures. I'm just showing some kind of pictures to show how the models are complex. This one particular model which we worked for Indian Oil, the second model, those structures pretty small. That was haunting them more than 2.5 years. It's a very small structure. That's a mixture structure, and before 3 to 4 years, when there is a problem in that structure, the entire boiler got blasted and it killed more than 29 people. So even though the structure is pretty small, the behavior is very complex. You can go to the next slide as well. Yeah. So on one hand, we have mathematics. On the other hand, we have experiments, and you have mathematical modeling, which is limited, and you have experiments, which is really tougher to do it. For that reason, we have computational methodology. So computational methodology purely relies on numerical methods. So in 1904 World Science of Conference, people decided about mathematical modeling. They worked on, discussed a lot on mathematical modeling. So when mathematical modeling were applied for complex models, complex physics, the bigger challenging they found is they were able to convert the physics into mathematical modeling. But the bigger challenge is how to get this solution mathematical. It's Einstein or even any other science modeling, which we do as well. Mathematical modeling is one of our but converting the physics modeling looks easy comparing models. So that is where another alternate for mathematics. Whenever mathematics becomes impossible, they want to devise another methodology which is called numerical mathematics, which we study in our engineering curriculum. So everything is linked. You have physics, you could have studied different subjects, something like fluid mechanics, heat and mass transfer, or even structural mechanics. I mean, these are nothing but physics. These subjects talks about physics. So they are very much linked with mathematics, particularly M3. And whenever M3 becomes limited, there is another subject called numerical method. Numerical method comes into picture, and with numerical methods, we are able to solve a lot of stuff. So the point is something like, as a person who works on R&D, I'm enjoying the application of mathematics into the real world problems. I'm enjoying numerical application in the real world problems. So if you want to get into R&D without mathematics, without numerical methods, nothing is possible. Mathematics is nowhere a tougher subject. It shouldn't be, because it is the fundamental for engineering. It is a stepping stone of engineering. It is the alphabet of engineering. It has to be simple. It has to be easy. So without mathematics, this R&D is impossible. So if somebody wants to get their career, set their career into R&D, they want to know the mathematics properly. And understanding the mathematics is not a challenging one. It is easy, because as a person who continuously utilizing mathematics into real world problems, I believe that mathematics is really, really easy. Yeah, you can go to the slide. So mathematics, on one hand, it is, limited. Experiments are challenging. So you want another alternate, which is computational modeling or numerical modeling. Yeah, you can go to the next slide. Yeah. So looking into these equations, one get frightened, more than Corona, but these has a meaning. So they are not a toughest equation. I'm training some candidates as well for my own purpose. But once the candidate comes into our office, like within a span of 1.5 months, they get trained, they get used to these kind of equations. They know what is the meaning of these equations. Obviously, they are able to derive those equations properly. So if you see these equations, they are in the form of partial differential equations. The first one states the conservation of mass getting conserved. This we could have studied in our 11th standard or even 9th standard. Mass neither be created nor be destroyed. So that concept is mathematically converted. If you talk about a concept that states a physics, if you say definition, that states a physics. Nothing is more than that. For example, in thermodynamics, if you talk about Kelvin-Planck statement, it states that heat cannot be moved from cold body to hot body. That is obviously true. We realized it. So a statement or a definition states a physics. Nothing more than that. You, me, everyone knows the truth. But what is a derivation? Derivation is converting that physics into a mathematical description. Likewise, the fluid dynamic concept is converted into mathematical description. So if time permits, if you are able to meet further, maybe I can explain these things properly. But these partial differential equation is a mathematical description of fluid mechanics. Yeah, you can go to the next slide. Yes, so let us get into CFD, like how the CFD process is done. So as time is running out, I'll just rush it up. So we have 3 different steps. One is called pre-processing, and we have certain tools with which we do all this pre-processing activity. Once the model comes into us, we take those models, we do some kind of cleanup activity, we do connectivity errors. If there are connectivity errors, we rectify those errors, and we heal the model. And if at all we need to add some kind of wind tunnel or anything like that, we add that. And after that, we do discretize, which is called meshing, and we do surface meshing as well as volume meshing. One called solving. I've shown some kind of mathematical description of the fluid mechanics, which is partial differential equation. So that equations are solved in a software called either Star Cesium or Fluent. Once that is done, we are taking those results, and those results are called post-processing results. So the result extraction and report generation is called post-processing. So pre-processing is the first one where we heal the model, and the solving is done where those mathematical equations are solved using computers, using a method called numerical method, and finally we do post-processing. So I'll just show some kind of work that we have done already. Here you can go to the next slide. Okay, these are some pictures which you can see meshing. So this is the first structure we worked for, again, Navy. There's a huge transformer which is mounted on this structure, and with the wavy motion, that heavy structure is imposed to a kind of big load. So these structures hold those transformers on a proper position. So how they are behaving statically, dynamically, when there is huge load on that, when there is a kind of even sudden earthquake, how they are behaving. For that reason, we worked on this particular model, and that you can just how they are discretized. Some kind of triangular elements. These elements are called mesh. You can go to the next slide. Yes, few slides, pictures where I'm showing how the models are meshed. So the first one is something like the furnace, the injector, the combustion chamber, the pump structures, multi-stage pump structures, multi-stage submersible pump structures. These are some kind of projects we work where I'm just showing what is mesh. Yeah, you can read the next slide. Yes, this is another furnace, and there is one thing called, another thing is called missile structure. When this missile is launched, how it is, overcoming the aerodynamic dragging, its own inertia, is it falling on the right place? So I just wanted to understand those kind of things. So for that, we made this meshing activity. So these pictures just show you how the meshing is done, how the meshing would be. You can go to the next slide. Fine. So this is a kind of idea how a CFD report should be. So we take a car, we put the wind tunnel, we did the analysis, and you can see some color plots for velocity, pressure, how the path line is moving over the car, and what is the level of CL, CD, everything is shown properly. This we did for Tata Motors. You can go to the next slide as well. Yes, this is a cabin cooling project that we worked for, again, Tata Motors, and that inner structure of a car is taken, a mannequin, a driver, a co-driver, 2 more passengers were kept inside the cabin, and we conducted an analysis, how the velocity is distributed inside the cabin, how the temperature was, and is the people are really getting comfort, what is the comfort level, and how the air is getting circulated. A lot of information we took from computational fluid dynamics. You can go to the next slide as well. Yeah, we did for DRDO. Like, we want to understand how the thermal comfort is achieved under the heavy truck. So for that, we conducted the under hood flow. So underneath the car structure, when the air is moving, is the airflow air flow rate sufficient to remove the heat from the engine? Will it create hotspot stresses on that zone? So that is, tested on that structure. Yeah, you can go to the next slide. It's almost 10. Yeah, this is one other project we regularly work on Cummins, where we understood how the after treatment methodology is there. This is a huge area, but again, we did one more analysis. But you can go to the next slide. Yeah, this is another project we work for Indian Oil. So maybe you can see the structure is very small, but this was really haunting them more than 2 years, as I already said. So you can go to the next slide. Like we introduced an injector, and you can go to the next slide and you can see how the injector was performing. So it is to improve the mixing of some hot condensate as well as the cold condensate. You can go to the, you can rush up the next slides as well. Yes, you can see how beautifully the informations are, taken. How the velocity distribution, how the velocity vectors, how the path lines, how the stress even, the pressure values, a lot of stuff, results were taken. There you can get it next slide. You can rush it. Yes, next one. See, in different planes along the fluid path, wherever you want, you can get the information. So that is the beauty of computational methodology. So experiments won't reveal these many things appropriately and so beautifully. On one hand, that was the biggest challenge of experiments, but computational methodology gives you an immense results about that structure wherever you want. There you can go to the next slide. Yes, such a beautiful results being taken. Even for temperature, you can go to the next slide. For pressure, you can go to the next slide. Next one. Yes. How the temperature is distributed all along that structure. So the temperature, huge temperature difference was causing thermal stress. And in fact, that is the reason why it goes blasted, like what happened with Columbia, Kalpana Chawla case. Again, you can go to the next one. Even the path line, how they are mixing, the hot and cold fluid, how they are mixing was appropriately taken. Yeah, you can go to the next slide. Yes, to be honest, this is not a technology that can be explained in half our time. It's a very lengthy subject. I just gave you a kind of glimpse for that. It's an ocean. I may give you a kind of few drops. To be honest, yeah, it is a very lengthy technology because we need to run across the history of human evolution. So it's very big thing. But I guess, as per my understanding, most of the information I've shared is gone across to you. And if you have any queries, you can ask me. Otherwise, thank you for your patience. Hello.
Hello, sir.
Yeah, it's 11 o'clock.
Okay.
Is it all right or?
Sorry, waiting for the questions. Yeah.
Participants can post their question in the chat box.
Questions from audience. Anything? I think no questions has been posted so far.
Okay, no problem. It's really a kind of tougher area, this competition. But one thing I want to share is like, one thing I want to share is something like, there are a lot of opportunities in this particular area in India as well as in abroad. So if somebody wants to start their career, in either CFD or FEA, you have tremendous amount of employment opportunities, even in India and abroad. So being a mother nation, UK has a hell lot of opportunities, and in US as well, or even France, Germany, these countries are countries where CFD is very much utilized. And India, starting from General Motors, Ford, Nissan, Chrysler, these are the major companies. Automotive companies, auto ancillary. These are the companies wherein you have a lot of employment opportunities for the candidates.
Okay, sir. Sir, Tanigal sir, are you ready? It's audible?
Yes, sir.
Hello.
Yes, sir.
Yeah. Okay,
Sir, Tanigal, sir.
Okay.
Yes, Tanigal. Yes.
Good morning to all. Myself, Tanigal Mura, Assistant Professor, Department of Mechanical Engineering. I would like to thank management, administrator, and principal ma'am for conducting this webinar. I would like to thank today's speaker, Mr. S. Nagarajan, Managing Director, Flow Explorer, Coimbatore. Thank you, sir, for your interesting and valuable, very informative session. My sincere thanks to Mr. Dr. V. Balaji, HOD Mechanical Engineering, Loyola Institute of Technology. My sincere thanks to all the participants from various colleges. Once again, thanks to all. Stay home, stay safe. Thank you.
Yeah, thank you so much for the nice opportunity. Thank you.
Yeah. Thank you, sir. The session is very nice, sir.
Thank you.
Participants, you have to fill the feedback form. The feedback link is available in chat box. Kindly fill the form.
Okay, ma'am.